Hello everyone. Welcome to this session on Conductometry part 1. This is Sarita, Assistant Professor of Chemistry from GDCW Begumpet. In our last sessions, we have seen the electroanalytical methods or techniques in which we have discussed about potentiometry and voltammetry, the principle behind those techniques and its applications. Now today, let us discuss about another technique, that is conductometry. Now before going into the topic, first let us see what is meant by electroanalytical technique or methods. So as we all know that these are the techniques that measure the potential, charge or current to determine an analyte concentration. And what are the different techniques we use here? We use potentiometry or voltammetry, coulometry, conductometry, and dielectrometry. So these are some of the techniques which come under electrochemical methods. So in our today's class, we are going to discuss about conductometry. So in this conductometry, I'm going to cover the introduction part, principle behind conductometry, important definitions and relations, measurement of conductivity, the instrumentation, conductometric titrations, advantages and disadvantages of conductometric titrations, and of course the applications of conductometric measurements. So first, let us know what is the definition of conductometry. So conductometric analysis, it is based on the measurement of electrical conductivity of the solution due to the mobility of cations and anions towards the respective electrodes. That means in this technique, what we are going to measure? We are going to measure the conductance, or that is electrical conductivity of that particular solution. And how this conductivity is measured by that is, we all know that the current is nothing but the transfer of electrons. So here, when we are doing this experiment, the electrolyte which is present, now it will undergo dissociation to give the cations and anions. And these ions, they will move towards the respective electrodes. So because of that movement of those ions to their respective electrodes, that means the transfer of electrons takes place. That is nothing but it is helping in the passage of the current. So in this conductometry experiment, we have to measure that particular conductance. So the electrical conductivity is entirely due to the movement of ions. And the ability of this ion transport charge, because it has to transport the charge from one electrode to the another, and that depends on the mobility of the ion. So the mobility of that ion, it depends on some factors such as the number of ions, the charge of ions, the size of the ions, and the temperature. So all these factors affect the mobility of the ion, because anions have to move towards the positive electrode and cations have to move towards the negative electrode. So that movement of electron, we call it as that is that movement of the ion, because it may be either cation or anion. So that depends on the number of ions, charge and size, as well as the temperature under which we are performing the experiment. Then the principle behind this is, it is based on the conductance of electrical current. The electrical current, it has to pass through the electrolyte solutions. It is nothing but similar to the metallic conductors. Now, this electric conductance, it is actually in accordance with the Ohm's law. Now, what is Ohm's law? The strength of the current passing through the conductor, it is directly proportional to the potential difference and inversely proportional to the resistance. So all these conductors, the current has to pass through this electrolyte solution, and that strength of the current which is passing through the conductor, it should be directly proportional to the potential difference. That means here we are taking potential difference as V and R is the resistance. So I is the current carried, which is directly proportional to V, that is potential difference, and it is inversely proportional to R, that is the resistance. So I is strength of current, V is potential difference, and R is the resistance. So the principle behind this is the current is carried because of the mobility of the ions, and that current should be directly proportional to the potential difference, and it should be inversely proportional to the resistance. And there are some terms where we have to first understand them before directly discussing the instrumentation and the application part. So the Ohm's law we have completed just now. Now what is conductance? Here it is I is equal to E by R. So you can take either V by R or it may be E by R. Now what is conductance? It is nothing but the ease with which the current flows through the conductor. So if the current is flowing fast through a conductor, that means the ease with which it is flowing through the conductor is nothing but conductance. And always this conductance will be reciprocal to the resistance. If resistance is less, then the current flows into the conductor very easily. If the conductor is having more resistance, then the conductance will be less. So C is equal to I by R. C is the conductance and R is the resistance. And the units will be ohm inverse, because the resistance, the units for resistant is ohm. Now when we are discussing about C, that is the conductance, it is 1 by R. Okay, that means ohm inverse, or it may be, we can also write it as mho, MHO, mho. Then the other term is specific resistance, that is rho. Now what is specific resistance? So that we'll see in this, that is the derivation part. And as we know that the resistance is directly proportional to the length, and it is inversely proportional to the area of cross section of a wire. So that means you can see R, always the resistance when we are talking about a cross section of a wire, the resistance will be directly proportional to its length, and it is inversely proportional to the cross section, that is A here. So if we remove this proportionality constant, we can write here as R is equal to rho into L by A. Now this rho is nothing but the specific resistance. Now if we are taking L, that is length of the wire, as 1 centimeter and area as 1 square centimeter, then R will be equal to rho. That means specific resistance will be equal to the resistance when we are having 1 centimeter length of wire and area as 1 square centimeter. So by this we can define the specific resistance as the resistance of 1 centimeter length and 1 centimeter square area of cross section, and the units will be ohm centimeter. Next term is specific conductance, or it is electrolytic conductivity, which is represented by K. Now what is K? It is just the reciprocal of specific resistance, is called specific conductance. Or we can also define it as the conductance of 1 cc, that means, or it is 1 ml of conductor, is called specific conductance. Now as we know that K is equal to 1 by rho. And what is R? R is equal to rho into L by A. This is the expression for resistance. Now, as in the definition itself, we have, I said that the reciprocal of specific resistance is called specific conductance. So what is specific resistance? It is rho. So K is equal to 1 by rho. But When we have this expression, that is R is equal to rho into L by A, or rho is equal to R into A by L. We have just cross multiplied it and we have taken rho to the left hand side. Now we need reciprocal of rho. So that's why we are taking the reciprocal of this. That is 1 by rho will be equal to L. This is also we are interchanging. So L comes to the numerator. So L by A into 1 by R. Now from 1, okay, this is the first expression, first equation. So here, what is 1 by rho? It is nothing but K. So K is equal to L by A into 1 by R. So this is the expression for specific conductance. And what will be the units now? It is L by A into 1 by R. So L by A into 1 by R means R is in the denominator. So it will be ohm inverse and centimeter inverse, because centimeter is length and square centimeter is the area. So centimeter will get cancelled. So one more centimeter will be remaining in the denominator. So it is centimeter minus 1. Or ohm inverse means we can also represent by mho dot centimeter inverse. So this is specific conductance. Then equivalent conductance. Now equivalent conductance, it is nothing but it is the product of specific conductance and volume of the electrolyte solution containing 1 gram equivalent of an electrolyte. Or we can also define this as the conductance of all ions produced by 1 gram equivalent of an electrolyte in a given solution is called equivalent conductance. So the conductance of all the ions which are produced by how much? 1 gram equivalent of an electrolyte in a given solution is called equivalent conductance. That means lambda is equal to K into V. It is a product of specific conductance and the volume of the electrolyte. So it is K into V, or we can write it as K into 1000 by N, where N is number of gram equivalents present in volume in liters. Now, if we write the units for this, it becomes ohm inverse centimeter square, which is gram equivalent inverse. Then we will be seeing the relation between the specific conductance and equivalent conductance. Now, what is the relation between these two? So for that, suppose if we are having any metallic vessel which is 1 centimeter apart, that is the side is 1 centimeter of that metallic vessel, and if we fill that vessel with some solution, and that vessel is having a cross section area of 1 square centimeter, and if we fill that vessel with the 1 gram equivalent of the electrolyte, so 1 ml of the solution is placed in the vessel which is having 1 gram equivalent of the electrolyte, then the measured conductance will be equal to the equivalent conductance, that is lambda will be equal to K. So specific conductance is equal to the equivalent conductance. Now suppose if we dilute that 1 ml which is taken in the vessel, and if we are diluting it into the 10 ml just by adding 9 ml of the pure solvent, then lambda will be equal to K into 10, because we are diluting it to 10 times, that is K into 10. So that's the reason we write the expression as lambda is equal to K into V. So what is V? V is the volume of the solution. So how to define this now? Equivalent conductance lambda is equal to specific conductance, that is K, into volume of the solution in ml, which is containing 1 gram equivalent of the electrolyte. So lambda is equal to K into V. Then what is the relation between molecular conductance and specific conductance. So it is also similar to that of the equivalent conductance. So here molecular conductance we are representing by mu V is equal to K into V. So molecular conductance is nothing but it is equal to specific conductance into volume of the solution in ml containing 1 gram mole of the electrolyte. So all these expressions they will be useful for us for solving the numerical problems. Okay. So first we have to understand what is specific conductance, equivalent conductance, what is the formula for calculating the resistance, and what are the units. So if we are thorough with those terms, then it will be easy for us to solve the problems. Then we will discuss about the measurement of conductance. How is that we are going to measure the conductance? So for that, here we are using a Wheatstone bridge method. So in this slide, you can see this is the conductivity cell which is placed in the test solution. So this C is written here. This is the test solution in which the conductivity cell is placed. And this complete test solution will be placed in a thermostat. So why thermostat? Because the mobility of the ions depends on the temperature also. So here we need to perform the experiment by maintaining the temperature. So constant temperature. So that is the reason why the conductivity, this one test solution cell is placed in the thermostat. And the conductivity cell is connected to a resistance box. Okay, a resistance, and the other wire is connected to a induction coil where the current is being passed into the solution. Now this resistance, this wire which is there, it is also connected to a long wire which is AB. So you can see this one AB, and this is the resistance box, and here this is telephone head. Now when the current is passed into the test solution, what happens? The electrolyte will get dissociated into ions, and these ions will be moving to the opposite electrodes. Now first what we have to do is we have to select one resistance, and then we have to touch this wire on this long AB wire. So we have to see where the sound, that is where the telephone head is muted, and then we have to note the distance also. Now you can see, so here what we have done is the solution for the conductance is taken in a conductivity cell, and then it is kept in a thermostat. The cell is connected to a resistance box R on one side and also a long thin wire AB. Now what we are doing, a known resistance R is taken out of the resistance box. And what current we have to pass? We are passing alternating current, that is AC current is passed through the solution with the help of that induction coil. Now the sliding contact D is moved on the wire AB so that minimum or no sound is heard in the headphone. So we need to move that wire on that thin AB wire such that there is no sound produced or no sound heard. So that point we have to take it as D. Suppose if we are taking as D on the AB wire. Now we can say that the resistance of solution by resistance R should be equal to the length BD by length AD. So by knowing all these values, that is R, AD and BD, so all this length BD we will be knowing, AD is also known, R is also known, because we are we are applying the known resistance to that. So thereby we can calculate the resistance of solution. So as we know that conductivity is inversely proportional to the resistance. So if you know the resistance, we can easily that is measure the conductivity. So this is how conductivity is measured. So what we have to do is we have to take a electrolytic cell where the cell is immersed in the test solution and that it is kept in the thermostat to maintain a constant temperature. And then the wires are, one of the wire is connected to the resistance box along with the long wire AB. Then the other wire is connected to the induction coil. And now when the resistance, known resistance is taken and we have to move it on the wire AB such that no sound is heard. So that point we are taking it as D. And then when the current is passed and when this length BD and AD is measured, even R is known, and from that we can find out the resistance of solution. So if resistance is known, then it is very easy to measure the conductivity, because conductivity is inversely proportional to the resistance. Then how to determine a cell constant? So why we need to determine the cell constant is, see, the electrodes in the cell, they won't be exactly 1 centimeter apart, or they may not have 1 square centimeter. So it is not that every time the observed conductivity is equal to specific conductivity, but it may be proportional to the specific conductivity. So that is the reason why we have to calculate a factor for the conductivity cell, that is nothing but the cell constant. So how to calculate the cell constant is, a cell constant when multiplied by the observed conductivity gives the value of the specific conductivity. So how to do that is, we already know that R, that is resistance, is equal to rho into L by A. Now, in that, we are taking this L by A as a constant. Okay, length of the wire by area of cross section of the wire. Now, when L by A is taken as X, so X is cell constant. So R becomes, that is resistance, is equal to rho into X, where X is the cell constant. So X will be equal to rho by, that is R by rho. Then cell constant is equal to, what is R? It is nothing but the resistance. And if you want to get conductivity, what we'll do? It is nothing but reciprocal of the conductance. So 1 by observed conductivity. R is nothing but 1 by observed conductivity into 1 by rho. This one rho is already there. So it is specific conductivity. Now if we interchange or cross multiply, the relation what we get is specific conductivity is equal to cell constant into this observed conductivity. So this is the relation between the specific conductivity and observed conductivity. So if we know the cell constant and the observed conductivity, we can find out the specific conductivity also. Now, if we have a cell constant, suppose how to calculate the cell constant if our solution N by 50 kCl at 25 degrees centigrade. Now, the specific conductivity is known. It is this one, 0.002765 mho. Then the conductivity is observed in the cell. Okay, then cell constant will be equal to the specific conductivity divided by the observed conductivity. So specific conductivity, already it is a known value which is given. And if we observe whatever the observed conductivity is there, that we have to substitute it here. So by dividing these two values, we will get the cell constant. Now, we will discuss about the instrumentation part. Now, instrumentation, so the instrument which is used to measure the conductance, we call them as conductometers. And they consist of the current source, the conductivity cells, and the electrodes. So current source, generally it will be an alternating current. Conductivity cells may be wide mouth cells, cells for reactions producing precipitates, and we have another type of cells which are dip type cells, that is which are directly dipped into the electrolyte. And these cells, what do they contain? They contain the electrodes. So current source. So as I said, we should supply AC current. So mechanical high frequency AC generator by Washburn, or the other one is relay oscillator by Taylor and Ackery, vacuum tube oscillator by Hall and Adams. And when this electrical potential is applied across the electrodes, so what happens is two processes occur. One is ions accumulate near the electrodes and the transfer of charge through the interface. So once when we apply the current into the electrolyte, as the electrolyte is undergoing ionization, and the respective ions which are produced, they will be accumulated to the opposite electrodes. After that, there should be a transfer of charge also. And here we have to apply only the AC current. So DC current is not employed because what happens is the electrodes become polarized, which leads to high cell resistance. So when there is high cell resistance, there won't be any conductance. So that is the reason why we should apply AC current only. Then the conductivity cells. The conductivity cells, they are made up of pyrex or quartz, and they are fitted with 2 platinum electrodes. They should be placed in a vessel containing, always they should be placed in a vessel containing water to maintain a constant temperature. And these cells are, they are of wide mouth cells. They are cells for reactions producing precipitates and dip type cells. So this is the conductivity cell which we use in our lab. So take that conductivity cell and dip it in the, that is the test solution. So connect these two to the conductometer and it will give the readings that can be noted. So this is the arrangement of the conductivity cells. So here you can see the one type where platinized platinum electrodes are placed in the cell and they are connected to the wires, or else the cell which is in this form also, 2 electrodes, they are connected to the wires. Then electrodes. So these electrodes are made up of platinum sheets which are of 1 centimeter square and are fixed. They are fixed at a distance of 1 centimeter. So the 2 electrodes, the distance between the 2 electrodes should be 1 centimeter. And the surface is coated with platinum black. So why platinum black? To avoid the polarization effect and also to increase the effective surface area. So that, and this, that is platinization of electrodes, can also be done by 3% chlorplatinic acid and lead acetate. So the electrodes usage depends on the conductivity and the concentration also. So when the concentration is low, then electrodes should be largely and closely packed. Now what are the various conductometric titrations? Let us see. So this is one of the applications where that is we can know the concentration of the test solution by performing the titrations, which are known as conductometric titrations. So in a conductometric titrations, the titrant is added from the burette actually. And the values of conductivity are noted down, and by adding 1 ml of the titrant, the conductivity value or the conductance will be changing, and that should be noted down. Since the measured conductivity is a linear function of the concentration of ions, 2 lines will be obtained which will intersect each other at a point known as end point or equivalence point. So what we will be doing here is actually, now this is the conductometer. Now here this is the conductivity cell. This is magnetic stirrer. Okay, the beaker is placed on it. Now we have to take a burette, okay, in which titrant is filled in the burette, and then we have to keep on adding 1 ml, 1 ml, and then we have to check the change in the conductance. So that is displayed on the conductometer. So after noting down the values, we have to plot a graph. So in that graph, we'll get two lines which intersect each other. So that intersection point is nothing but the end point or the equivalence point. So that we'll see now. See, this is the conductivity cell. This is a solution, test solution. A magnetic stirrer is there. And this is a burette which has to be clamped to a stand. And the conductivity cell is connected to a conductivity meter. Now, there are different types of conductometric titrations, such as acid-base or neutral titrations, redox titrations, precipitation titrations, replacement titrations, and complexometric titrations. So, best thing is actually we can study acid-base titrations very easily by this technique. Now, in this acid-base titrations, again we have different types. Those are strong acid, strong base, that is HCl versus NaOH as an example. Then strong acid, weak base, HCl versus ammonium hydroxide. Then weak acid, strong base, acetic acid versus sodium hydroxide. Then weak acid versus weak base, that is acetic acid versus ammonium hydroxide. So let us see all these four different types of titrations now. The first one is strong acid versus strong base. So what is the neutralization point in such type of titrations? And here we are taking an example of HCl versus NaOH. Both are strong. So HCl and NaOH. So in the aqueous medium, they will dissociate to give ions, that is H plus Cl minus and Na plus and OH minus. Now, in this type, when we keep on adding, so here HCl is taken in a beaker and NaOH is filled in the burette. And we have to start the reaction by transferring 1 ml of NaOH from the burette into the beaker and then check the conductance, change in the conductance. So all those conductance values we have to keep on noting down for each 1 ml of the solution of NaOH which is added into the HCl. Now how after that, if we plot a graph, it looks like this. So by taking volume of base on x-axis, conductance on y-axis. So we will get two lines. One is this one and the other is this. Okay, so these two lines are intersecting at this point, and that point, when you draw a perpendicular onto the x-axis, we can know the exact volume of base required to neutralize the acid. So in this, you can see first at the starting of the reaction, the volume of the base or the conductance, because in the beaker it is HCl. So HCl is dissociating to H plus and Cl minus. So because of the mobility of H plus ions and Cl minus ions, the conductance will be more. Okay, so that's why we are starting from the highest level of the conductance. So conductance is more because of the H plus and Cl minus ions. So as the NaOH is being added to the HCl, what is happening? You can see the conductance, the curve is going down, it is decreasing. That is, the conductance is decreasing as we are adding the volume of the base. So why it is decreasing? Because when NaOH is added, so it is dissociating to give Na plus ions and OH minus ions. So all those Na plus ions, they are going and they are combining with Cl minus and it is giving rise to NaCl. Okay, And the remaining ions, what are left? They are H plus ions. So because of this formation of the salt, the conductance is slowly decreasing. And after some particular point, what happens is we can notice that the conductance is increasing. So why it is increasing now is, suppose all the NaOH, whatever we have added, now they have reacted with HCl. Now there are no HCl, that is H plus and Cl minus ions, which are left over in the beaker to conduct the current. Now what is left? The NaOH, which is falling into the beaker. So due to that NaOH, that means it which is producing Na plus and OH minus ions. So because of that ions, again the conductance will increase. So this is how the curve, conductometric curve looks like for strong acid and strong base. So first the conductance is high because of H plus and Cl minus ions. Slowly the conductance decreases because of the addition of NaOH, and then after certain point again the conductance increases because of the Na plus and OH minus ions. Then the other type is strong acid versus weak base. So strong acid HCl we are taking, and weak base is ammonium hydroxide. Now what is happening here, you see, the ammonium hydroxide which is there, it will react with ammonium ion, will react with Cl minus to give ammonium chloride. And the conductance, now here ammonium hydroxide is taken in the burette and HCl is taken in the beaker. So now here from the burette we are adding ammonium hydroxide. So first thing is, again you can notice there is a fall in conductance due to the replacement of hydrogen by ammonium ions. So first it is high, the conductance is high. Why? Because of the conductance of H plus ions. Now as we are adding ammonium hydroxide, all the H plus ions are replaced by the ammonium ions. Then after certain point, you can see that the conductance remain constant. So why it is remaining constant is due to the suppression of ammonium hydroxide by ammonium chloride. So here when ammonium ion is combining with Cl minus, we are getting ammonium chloride. Now this ammonium chloride, what it will do is it will suppress the dissociation of ammonium hydroxide, which is nothing but common ion effect, where ammonium chloride ion is suppressing this dissociation of this ammonium hydroxide. So thereby what happens is after some time we do not find any increase or decrease in conductance. It is nothing but a constant graph we will get. So in this you can see, so first this is because of HCl, conductance is high. Slowly all the H plus ions are replaced by ammonium ions. So therefore the conductance is decreasing. Then after some time the conductance will not increase because due to the suppression of ammonium hydroxide by ammonium chloride. And the point where these two lines meet is here. And if we draw perpendicular onto the x-axis, that gives rise to the concentration, that is volume of base, which is required to neutralize the acid. Then weak acid, strong base. So weak acid is acetic acid, strong base we are taking sodium hydroxide. So they will give rise to acetate ion, sodium ions and water. So as it is a weak acid, okay, so first initial decrease in conductance followed by increase due to NaOH and steep rise due to excess of NaOH, you can see here. So first what happens is, as we add, NaOH is taken in the burette and acetic acid is taken in the that is the beaker. Now when we are adding sodium hydroxide, so acetic acid is reacting with the sodium hydroxide, that is Na plus, and it is giving rise to sodium acetate. So that is the reason why slow increase in the conductance is seen, because it's a weak acid. So until all the H plus ions are replaced by Na plus ions, now the further addition of NaOH results in sudden increase in the steep increase in the conductance value because of the strong base, that is strong base where it is releasing OH minus ions. So this increase is due to the OH minus ions. The last type is weak acid versus weak base. So here weak acid is again acetic acid we have taken, weak base is ammonium hydroxide. Now again the increase in conductance first is seen because of excess of acetic acid which is present, and then the constant curve becomes constant because of suppression of ammonium hydroxide by acetic acid. So again the ammonium acetate which is formed is suppressing the ammonium hydroxide. So that is the reason why again we will get a constant graph. So first there will be an increase in the conductance because acetic acid is a weak acid. So it is starting from low conductance. So as we add ammonium hydroxide, slowly the conductance increases. And then because of this suppression of ammonium hydroxide by the acetic acid, the curve remains constant. So the end point is nothing but where the two lines meet and the point, the perpendicular is drawn onto the x-axis, which gives the volume of ammonium hydroxide required for the neutralization of this weak acid, that is acetic acid. So these are the 4 different types of acid-base titrations and the conductometric curves. The next is the precipitation titrations. So here we have taken an example of potassium chloride versus silver nitrate. So as we know, the reaction between these two is Ag plus ions react with Cl minus to give AgCl as a precipitate, K plus, that's potassium ions, and nitrate ions. Now as we go on adding the volume of silver nitrate which is taken in the burette, KCl is taken in the beaker. So what is happening? The first actually the curve, the conductance remains constant. Then after, because all the Ag plus which is being added, it is combining with Cl minus to give silver chloride, that is a precipitate. Now after the formation of the precipitate, now that means all the chloride ions have been combined with the silver ions. Now the leftover NO3 minus which is being added, or the silver nitrate which is being added into the solution. So because of the mobility of these ions, the curve increases. That means the conductance starts increasing. Now these two curves or the lines where they meet, that point, that intersection point is taken as the volume of silver nitrate used for the precipitation of, that is, it is used for the formation of AgCl on reaction with the potassium chloride. So this is about the precipitation titrations. So hope you have understood the different types of conductometric titrations. So in conductometry, it is very simple where we are going to measure the conductance of the test solution. So in that, we have seen the conductometric titrations, which are acid-base titrations. And in that, we have seen strong acid, strong base, strong acid, weak base, then strong base, weak acid, and weak acid, weak base. And then another titration, which is the precipitation titrations. So all these are very simple to conduct also. So in the next class, we'll see some more applications of the conductometric titrations. Thank you. Thank you for watching.